Hello, everyone, and thank you for joining us today. Welcome to our first webinar of the year in our Testing Tactics webinar series. Today's topic is testing protection systems in the real world. My name is Michael Fleischer, and I'm the digital marketing analyst for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Guillermo Falquez, Relay Applications Engineer. To assist with the question and answer session, we will also have joining us Sugosh Kuber, Applications Engineer, and Abel Gonzalez, Senior Applications Engineer. All right, let's go ahead and get started. Thanks so much for joining in today, Guillermo.
Thank you, Mike. How you doing? So today we're talking about testing protection systems in real world, some challenges and recommendations. The way I want to do it and the objective of this presentation, it's to provide new technicians and engineers a personal framework, practical advice, and recommendations for testing protection systems. This is coming from my perspective in my years of being in the field as a field service engineer and testing not only relays, but different kinds of electrical equipment. The way that I went about to dividing testing a protection scheme is I divided into 3 sections that we're going to go into. It's going to be preparation, number 1, site arrival, and then actual testing. And then at the end of this whole presentation, I want to give you some testing tips or some practical advice that I would have liked somebody to tell me when I first started my career. So I'm just sharing it with you to, hopefully it'll help you out to understand things or better understand something that you already knew. So going into preparation, this is, I think, for any field service engineer or technician, one of the biggest thing. You get a call and you're like, hey, we need you to go tomorrow to this, and you're like, oh, but I didn't prepare. I haven't done this, and I devoted a lot of slides on preparation because I think it's one of the most important things to be prepared for a job before you even show up there. So let's say you get your call and you're like, okay, we need you to go and test some relays. One of the first things that you have to know is what type of testing are you doing. Acceptance testing, it's one of the types testing that you would do to a relay, which really mainly has to do to making sure that the relay that got shipped to the customer fulfills the expectations from the specifications that the buyer provided. So for something like this, you usually test, your inputs, your outputs, your communications. You would do basic element testing, maybe. So these procedures are usually the ones supplied by the relay manufacturer. So they're very basic, and you could do a quick bench test to do these tests. It's not a big deal. It used to be back in the day, utilities spent a lot of money into making sure that every single function and every single element on a relay would have to work before a utility would purchase these relays. But in my experience, it has changed a lot more as microprocessor relays have become more and more the norm within the industry. Another type of testing that you would have to do, it would be commissioning test. And these are site-specific tests. This is probably the most important and most stringent test, not only the relay, but your whole protection scheme, the whole application that you're testing will have to go through. So you would really have to test not only that the IO works, but that the logic, the test logic and the functional test of your breaker, your motor, your transfer scheme, that everything works together. It's a system view and it's a system test. Not only would be a relay test. So you would check your status, your metering, the event recorder, the communications, date and times, everything is set up and ready to go, and you'll have a full system test. Obviously, this will require a lot more time than, let's say your boss, when he calls you and say, oh yeah, this is a one-day job. It's like, no, not really. This is a more stringent test. And the most important thing is you're testing the application of the protection, the application of the relay, not only the relay itself. Then you could do maintenance tests, which have to do more with in-service checks. This is a relay that's already installed, and you're verifying that there hasn't been any changes on the settings. You could update the firmware on this or in the relays itself. If there is any service bulletins, you shut down the machines, and then you could do all your maintenance checks. I put test DIOs and do your trip checks. Not so much because the memory of the relay or the logic will change. It's mainly in the mechanical sense. You want to make sure that the wiring between the relay and the IO still operates, that there is no loose connections, that everything from the relay to your trip coil is still working, still in service in the physical sense, not so much in the a microprocessor relay world, which is not going to change. That memory is not going to change. In the electromechanical world, on the other hand, then this is where you're still checking that the relay is under calibration and is still operating, because obviously you're going to have springs, you're going to have all these mechanical devices that come together to make up that relay that change its their elements. It's just normal wear and tear on the devices, and you're checking on that. You could do forensic or troubleshooting testing. This is when an event has happened and you're checking for the security and the dependability on the relay. So you're making sure that if the relay trip, you understand why the relay tripped, or if it did not trip and it was supposed to trip, you're trying to understand why it didn't occur. So this is when you go to your event recorder, your data logs, and you try to recreate the event, because maybe that will lead into changing settings or adapting settings or adding settings in order to prevent that anomaly event to happen again. Another thing to know when you're going, hey, am I just bench testing this thing? In that case, the customer could ship you the relay and you're just doing it on your desk. If you're doing an acceptance test just with bench testing, or is it a relay that's installed in a piece of switchgear? In that case, you have to bring more equipment. You have to bring probably test paddles. We're going to go into defining the area of protection. So when you go out there, that lets you know what type of tools and what type of things you should bring with you when you do the testing. Are you doing any special application testing, like end-to-end? Let's say you're doing line differential testing, where you require 2 test sets on either side, and you need communication in between. You may need a GPS depending on the transfer scheme in order to sync up the time for both test sets. So that requires more equipment. So let's say you don't have that equipment available and they tell you, hey, we need you to go tomorrow. You could stop. Hey, man, everything they're saying here is for a line differential test. I'm going to need more equipment than what I got in my truck right now. Let's say you're doing dynamic test. Dynamic test is when you have a ComTrade file that saves the voltages and your currents into a computer file. You upload that into your relay test set. The relay test set converts that file into actual currents and voltages that you replay them to the relay in order to see its response. So in that case, you need to know, hey, I'm doing dynamic tests. Do I have the file with me? Those are the things that you have to think when you're preparing to go to the site. Another test that you could do is recloser testing, and the quirkiness on this one is depending on the relay test set that you use, you may need a separate box or a separate interface between the relay test set and the recloser controller. So that's another thing that you have to keep in your head. If you're, let's say, testing a recloser, what interface or what other accessories do I need for my relay test set? And lastly, and this is where probably the future of relay testing, there's already prototypes on this, and it's virtual testing. And this is where you have in the cloud a virtual relay test set and you have a virtual relay, both on the cloud, and you're able to test that relay from you're able to test that virtual relay from a virtual test set. And there's already prototypes out there that you could look. There's some papers out there, so you could start looking into that. But that's probably where the industry is going. Next is defining your testing responsibilities and the area. So for this, we're gonna make use of this simple 3-line. We have a breaker over here feeding a bus, a main breaker. Then you have your CTs right here, some test switches. You got a relay, a test switch for your voltage, and this is your PT. So we're gonna go through this example so we could see the different areas of responsibilities that you could have. This is a schematic for that breaker. This is the DC controller schematic for the breaker. And defining, first of all, you have to be aware of that there is not only a relay when you talk. When we're doing that, let's say you're doing a commissioning test, you have to be aware there are different devices besides the relay. In this case, it could be a breaker, a switch, fuses, all these things that make up your system. So this would be, in this case, it would be the breaker. You have to be aware how the relay interacts with the breaker. Know the location of the outputs of that relay as they are electrically located, and how it controls the breaker itself, how it trips it or closes, whatever the relay it's doing. Let me see. There you go. You got to know that other things that are in the system is your instrument transformers, your PTs and your CTs. Know the location, know what they do. All the interconnecting wiring between your input signals, in this case your PTs and CTs, and to your relay. The DC control, the power supply feeding DC power to the breaker control scheme. And then after you are aware of all the components that are part of this scheme, then you start to ask the questions, okay, but what am I responsible for? Am I only testing the relay? In that case, am I only doing a bench test? Or am I testing something that's installed? And am I testing now from the test switch into the relay, which is one of the easiest way, having a test switch installed, and then you test from this test switch into the relay? Or you could test from the shorting block on your currents, and the secondaries, and or from the secondary of your PTs, from the fuses all the way down. In that case, you're testing all the secondary wiring from the secondary of the PTs all the way down to the relay. So what you're responsible and what you're checking, it becomes bigger. Or you test the CTs, the PTs, and the relay. In that case, you're checking the whole thing. So that requires more test equipment. Now you need a CT test set, a PT test set, in addition to a relay test set. Or you could test the whole scheme, including the breaker scheme. Then you do a functions check. You make sure that every single ladder into your scheme functions as properly, all the lights, your trip coils, your closed coils. Now you're testing the breaker itself. You could do your high pot test, your contact resistance test, your bottle integrity if it's a vacuum bottle breaker, etc. So it is best to be aware that just because you're a relay tester guy, it does not mean that you should not be aware, or the best testing guys are the guys that are aware of the whole scheme, of everything of what's happening. You don't have to be an expert on every single little thing, but you should have an idea of what's going on around you in the electrical world. The types of relays that you could be testing, I'm only going to talk about electromechanical and microprocessors. There is solid state relays, but usually solid state relays were made as a direct replacement on electromechanical relays. So I'm in the instance of time, I'm only going to talk about electrical and microprocessor. Things to keep in mind when you're testing an electromechanical relay, everything from a preparation perspective. Is this a single or a multi-phase relay? A single or a multi-function? Am I only doing testing but not calibration? I personally have done a lot of testing on electromechanical relays, but I have not done any calibration. I try to stay away from that because it's a science on its own once you start tinkering with the relays. So it's good to know what your responsibility is. Typical things that you would check on a 5051, which is probably the great majority of the relays out there. You're going to check your tap setting, which is your pickup, the curve that it's using, and the time delay on it. On microprocessor relays, you're going to check. You're still concerned with all the things above, but the settings file responsibility. You get the call, hey, I got to test the relay. Hey, who's responsible for the settings file? Are we responsible? Is our firm responsible for the settings file, or am I get it when I'm on site? Can I have it before that? Am I testing the as found and the as left settings? What exactly is my responsibility when it comes to microprocessor relays? Again, single or multifunction, the logic testing. Sometimes testing the actual elements and the protection functions becomes the easier thing, but when you talk about the logic and all the different combinations or permutations of logics that you could have, that becomes a really bigger challenge than the actual testing. And that's something that you have to keep in mind when you talk to your boss and be like, hey, I'm being sent to test the relay, but hey, I'm not testing just the elements. That's the easy part. It's the logic and how it encompasses the whole application that could become a bit tougher to test, and something that will require more time. Are you testing the communications between the devices, between the routers, the servers? I mean, if you're doing that's going to require a lot more time. So you have to know what the customer or the end user expectations are of your test, and you also got to know what you're testing as far as how much money you got paid to go out there and do it. And for both, are they draw out or fixed? That's might make your life easier, because if they are draw out and you could pull the relay out without disconnecting or shutting down the gear, that makes matters easier. In the electromechanical world, it was really easy. You just pull the test switches down and you pull the relay out, and the gear could stay powered up. There are some electromechanical relays that you could draw them out to, and the gear doesn't have to be shut down. Or if they're fixed, then, hey, does the customer know that I have to shut down the gear in order to test these relays? Or if they don't have test switches, if they got test switches, then you could isolate it, but they will have no protection. So things like that, those are questions that you have to ask, because a lot of people don't know that this has to happen. Are they connected through the front or rear? And by front, I mean, do you have test switches? Because if you don't have test switches and you have to connect from the back, then you really are going to need a shutdown, because you're going to pull those wires out. You could isolate them, maybe your currents, but your voltages, you might not be able to do that. So things to keep in mind on how the testing goes around. Some tools for the trade that I think are important. If you are an engineer or a technician, you have to have a basic knowledge or basic understanding on electrical theory. Know your phasor diagrams, know how a three balance system works on looking at a phasor diagram, different faults, how they look in a phasor diagram. Those are things that will help you troubleshoot and understand what's going on. You can't, at least with microprocessor relays, you can't get away without knowing, at least to some extent, about symmetrical components. One thing that I see again and again in the field is the lack of understanding on rotation and phase sequence. Usually all the rotation, it's counterclockwise. All generators turn counterclockwise, at least in the US. It's the phase sequence that changes. Is it ABC or ACB? For those, that's just how the wires are connected, not how the generator it's actually turning. So keep that in mind. Those are little things that a lot of people get hung up on, and it's good that you understand the difference. You don't have to be a protection engineer, but I think it does help you if you, as you progress in your career, have some understanding on protection coordination and looking at time current curves. Understand that, this is a cable damage curve. This is a transformer damage curve. It looks like this. This is how a 5051 looks. I mean, these are all things that if the spider senses come in when you're testing a relay, and it's like, this is not making sense. What did the engineer intend to do? Having this practical knowledge, you don't have to know the theory behind it, but having a practical knowledge and knowing how this works, and you could see in a graphical way the intent of the engineer. IEEE device numbers, that should be lesson number 1, but you're going to learn that if you're in this field, you're going to learn that really quick. If you're an engineer, at least the per unit system, I think it's very, it would behoove you to understand how the per unit system works and why we use it and how it's being used to tell transformer impedances, short circuit levels. There's different places within the industry that uses the per unit system. So having a basic knowledge as an engineer will help you. Knowing drawings, we have a slide on drawings, the 1 lines, the 3 lines, schematics, wiring diagrams, knowing how to traverse through them, knowing where to go depending on what you're looking for. It's a tool that you should have. As a technician, as a guy, these are tools that, especially my multimeter, never leave home without it. You start collecting things as you go. Relay manuals, start having a library of Libre manuals and collect them. Make sure that your equipment is calibrated. Your lockbox, locks, a cart. I used to work in New York City testing relays or testing equipment, moving stuff in and out of my truck. Having a cart, it took me a year to realize, hey, I need a wheel cart. Not the sharpest guy, but this is a very good thing to have. Wire, some splitters, extension cords. Now, how you're connecting to the relay, there's different medias that are used, have the software that the relay use, test paddles. So in order to connect to your test switches, this is for a GE, this is for an ABB electromechanical relay, or if you're connecting to test switches, have the one that's needed for the application. Make sure that you have what you need. Now, knowing your relay tested and the software that you have, it's another thing that you should be you should always keep in mind. What are the capabilities of the tested that I have in my truck? How many channels are there available for voltage channels and current channels? Are they going to be enough for the test that I'm doing? This one right here, it's actually a single phase test set, but we have 3 of them. Knowing that you could daisy chain them and get a 3-phase test set and a total of 6 currents, if you're doing a transformer differential. But if you're testing an electromechanical relay that's only single phase, then you only need a 1 single phase unit, and you don't have to bring the big heavy test set. So know the capabilities and the equipment that you have. Let's say you're testing bus differential, and you have a low impedance bus differential relay, and you want to test different scenarios that requires you to have more current channels than 1 test set could do it. Knowing that you could daisy chain them and that you're going to require 2 tests to get 12 currents, keeping that in mind will help you. Going into the software, knowing that the testing tools that are available, really all relay tested softwares, they have a certain amount of tools, and by that I mean you're gonna have like a ramping tool where you ramp the voltage, the current, the phase, or the frequency, or all of them. How a fault test works. Timing tests, impedance tests, sequencers, differentials, fault calculators, relay test templates, knowing all the different tools that the software provides you, and understanding, okay, if I'm testing this element, I think the best way to test this element, it would be with the sequencer tool or with the ramping tool. So it's very knowing how the tools work and knowing how to apply them, it's something that will help you as you progress. So understand the relay software. Being on the manufacturing side of testing equipment, I could tell you a lot of the problems that are in the field could be solved by updating the firmware and the software. Having the latest firmware and software on the test equipment will solve a lot of the problems that you have. And making sure that you have up-to-date calibration on your equipment. Some accessories that you could have, make sure that you have the right accessories, enough cables. These are current cables, these are for voltages, these are for IO, having enough depending on the type of testing that you're doing. Having a dedicated controller. There are some nuclear sites that you're not allowed to bring a laptop or pull out information. You know, different test sets have dedicated controllers that you could use directly with the relay test set. That way, you don't need a laptop in there. You could just use it using the dedicated controller. Having some lugs, some jumpers. This is an example of if you're doing end-to-end testing and you need a GPS to synchronize the test sets. This is the GPS and the receiver. This is an example of, let's say you're testing a recloser and you need an interface that goes from the relay test set to the recloser controller, and you need an interface. You got to know, hey, I'm testing a recloser, know the capabilities and what's needed for the test set to do that test. Next slide. Then you go into your drawing reviews. Like I said, some of the tools, one of the tools that you need is knowing how to read drawings, knowing how a one line works and what the one line is telling you. It's a high level system view, and different one lines give you different information. If you're looking at a short circuit study, the last page on a short circuit study, at least the ones that I've seen, is usually a one line of the system, but that one line will tell you things like impedance, available short circuit current. This one in particular, this one line is one line of the protection scheme. It tells you the relays and what functions are available. So being able to capture that, to see that. Then you have your three lines where you have a wiring on how the system works. Then you have your schematic that tells you a functional view of how everything interacts together. Knowing which drawing to look and how to use it depending on what you're doing, it's half the battle, you know. And knowing also how the same component is seen in the different drawings. In this case, you're looking at the relay. You know, in the one line, this is how the relay is portrayed. In a three line, it's like this. On the schematic, it's going to show you like this, your IO. So knowing, depending on what troubleshooting, where to look, not only the type of drawing, but the location, and have an idea. It's things that you have to keep in mind. You know, where your CTs and PTs are located. So this could help you to look at the polarities on the PTs and the CTs. Maybe you don't see it on the one line, but you may see it on the three line. You obviously don't see that on the schematic. You know, and your electrical isolation points. You know, in the system view, knowing where the primary power is coming in. Am I isolated using primary power? On my three line, knowing where my test switches are, or the shorting blocks, or the main breaker, where those electrical isolations of primary and secondary power are, those are good things. On your schematic is usually DC control. Usually you have a knife switch, or you have some plug-in fuses that you could take out to isolate the power. Being aware of that, it's something that you should do to prepare for the job. So you know if you're electrically isolated even before you go there. If you have a chance to have a coordination study, usually they send you either a settings file or they send you a coordination study. You know, have a one-line review. Do the settings make sense? when you look at the coordination, this is a miscoordinated curve. Do they make sense? Did the engineer intended for this to be miscoordinated? Maybe this is a molded case breaker and the curve cannot change. Keeping those things in mind as you're reading the coordination study will allow you to understand the intention of the engineer. The relay configuration. Now you have, let's say you have the settings file. That's the polarity on the CTs and the PTs. Are they according to the relay manufacturer? Do they have their recommendation? If they're not, do they make sense? Was that the intent of the engineer? All these are things that just by looking at the drawings you could pick up, and before you're even in the site, you have an idea. Oh, I'm going to have a problem with this, or I'm not going to have a problem with this. Elements that need to be tested. Do the elements match the application? If you're going to test a transformer, you're not going to expect having a motor protection relay in there or motor differential. You expect a transformer differential, a transformer relay, and all the elements. Do they match what you're trying to protect? When you look at the logic, either your torque control or your flex logic or whatever the logic is called for the particular relay, are there any impossible conditions? Are there any elements that are not mapped to an output or an output that's not mapped to an element that's enabled? Things like that you could do before you even show up to the site. When you look at the wiring, know where the IO is on the relay, and if they're mapped correctly to, let's say, in this case, you're looking at a closing coil and a tripping coil and a breaker, knowing that that particular output, it's mapped and it's the closing coil for the breaker. The same thing for your tripping coil, for your trip logic. All that stuff you should have. You could do a review before you show up on the site. And at the end, make sure that you have the contact information of the engineer in charge if you have any questions. So that's something that you should have. Moving on to site arrival. So now you got to the site, and can I just start testing? Well, the answer is no. If you want to be good and you want to hit the ground running, make sure that you have the contact information of the customer or the representative that you're supposed to talk to. Be professional. Have your appropriate clothing and PPE. I think that the industry standard now is an 8-color shirt and pants, hard hat, safety glasses, gloves, hearing protection, and boots. I think that would be the basic. I show up to the site wearing that. Then you could add, your 40 cal suit and all that, but your basic tools or your basic wardrobe should be that one. Make sure your safety training, you're up to date with your OSHA training, site-specific training, drug testing, etc. Make sure that you have that done. And if you're like me, if I don't have food or water, I cannot think. So sometimes, or most of the times, all this equipment is in a remote site in the middle of nowhere. If I don't have food and water, I cannot think. So I have to prevent that and always have that available. Once you're with the customer, what to review, the physical device locations, my isolation points. Now walk them through with the customers. Don't just assume that you looked at them in the diagram, in the drawings, and that you know where it is. One thing is looking at the drawing. Another thing is seeing the device in real life, seeing that everything is locked out, tag out, physically see the switches open. Be aware of your surroundings. In the Army, they used to have this concept that they would drill it to you, situational awareness. Be aware of your surroundings. I was at a data center once. We were doing maintenance, and this new kid was on the site. He assumed that all the gear was shut off, and he leaned into a piece of switch gear, and he tripped a breaker by leaning by it. I was at another site. When you have those big jackets, the big guys, the jacket got caught on the control switch of a breaker, tripped the breaker. It's having a lack of situational awareness and not knowing what's happening around and what's live, what's not. Become used to that situational awareness. IO isolation, your trip circuits. If you have, we're going to talk about test switches. Knowing which points on your test switch go to the trip circuits, and isolate your trip circuits before you do anything else. coordination with other vendors. Usually when there's a shutdown, you're not going to be the only game in town. There's going to be other guys out there doing different things, different vendors. You got to coordinate with that. Know the restrooms. I had a lot of customers, they just, okay, you're doing your relays, goodbye, and you don't even know where to go to the bathroom. Things to keep in your head. Once you do a peers review with your own workers, let's say you're not going alone, but you're going with a bunch of guys testing other stuff, you know, work through the work assignments and what everybody is doing and coordinate. Let's say one guy is testing the PTs and he's doing PT testing, and you're on the other side of the PTs testing the relay. You want to know if the other guy is putting voltage on that side. So know where it goes back to knowing your area of testing and being aware of that. You should coordinate that. Then now getting into the actual testing of relays. You know, the first things that you do, it's a wiring check, and test switches, at least for relay guys, it's your best friend. It's the easiest way to test the relay. It's an easy way to isolate yourself from the rest of the world and just be you, the relay, and the test switch. But if you don't have a good understanding on how test switch works, you're gonna have problems, at least at the beginnings. At least in my experience, and this depends on each individual site, so this is not a written law, but usually black handles are your voltages and your currents, and anything in red, it's your trip circuits. And usually the way that I've taught and the way I teach and the way I learn is you open up your trip switches before you open up your voltages and currents. Why? Because let's say you start opening your voltages and your currents. Now that relay sees, let's say you only pull 1 voltage. Now your relay is going to see an under voltage condition on phase A, and it's going to trip. But guess what? You left your trip circuits closed, so it's going to trip the breaker when you did not intend to. So the red switches go out first to open, but the last ones to close, especially on electromechanical relays. That's something that you have to keep in mind. Make sure that if you have test switches, that they have test jacks. Those are these guys right here on the red rectangle and right here. These are points of isolation. When you have a test paddle, you would put the test paddle and will isolate, physically will isolate the top points from the bottom points. On your currents, it will isolate the currents will be short circuited by this test switch right here. The bottom handle, as it goes down, it shorts out the currents coming from the CTs on the bottom. So one thing to keep in mind is, especially for currents, make sure that the top wires go to the relay and the bottom of the test switch goes to your CTs. For voltages, it's not that important, but at least for currents, it's imperative that the top goes to the relays and the bottom goes to the CTs, because that's the way physically the test switch it's being used and how it's being shorted. Confirming that the shorting terminals are used for currents and the voltage terminals are used for voltages. Sometimes I also used to work in my past life with a switchgear manufacturer, and sometimes you got a new guy building wiring switchgear and he doesn't know that you know, these are for currents and the other ones are for voltage. And then you're the field engineer. These are things that you got to catch and keep in mind. Don't assume that the guy who built it knew what he was doing. I'm going to pay special attention to the shorting blocks because it's safety wise. This is one of the most important things when dealing with CTs. Understand the purpose of a shorting block. Knowing the grounding, where the location on the grounding is. So this is your shorting block right here. Usually I've seen CTs either grounded at the shorting block or at the CTs themselves, but it's usually on the CT side, not at the relay side. Confirm the installation and the removal of the shorting pins. If you've never seen a shorting block, this is how it looks. Your currents from the CT come in. This is your return, and then they go to the relay, and then you short out the currents. If you want to isolate the relay or your meter, you use these 4 screws to short them out via this bar right here. I was at a site in New York City, a very prominent newspaper. The whole transformer went on fire. And this is how important it is, because this is real life what happened. The whole transformer blew up, went on fire. The relays didn't do anything. All the settings were correct, blah, blah, blah. It took us half an hour to realize that the shorting pins on all the relays at this site were left on from commissioning. So the guys always saw a voltage because you don't use shorting pins for the voltages. So the relays show voltage. So everybody assumed, oh, the relays must be fine. But all these shorting pins were left inside. So the relay was not seeing currents. So that transformer blew up and it went on fire because somebody forgot to pull these shorting pins. Maybe they did not understand how it worked, but we're going to go through it. Let's say you're at a site and you want to isolate the relay using the shorting block. Usually, the one that grounds this pin, it's left in there. Or at least that's my practice. That could change depending on the site. But usually, I leave that screw in because this is going to be the screw that's going to ground all the other currents. So we're going to go through the procedure. You put the first pin, which is the one that goes to the ground. Then you take another pin, you take it out of here and you put it in here, and then you short it out your C-phase current. So now your relay doesn't see C-phase. Your current is physically being shorted via this bar. Then you go in and you do your B phase, you put the screw in, and now you're shorting B and C phase. And then you do your A phase, and now your relay is completely isolated. And then you could come over here if you want, and you could inject from your relay tested currents into your relay. Now you have to take it apart. You don't start with the voltage. You don't start with the grounding screw. You start with the A phase again. So the last one in is the first one out. You take this screw. Obviously, basic electrical theory, voltage, you don't want to short them out, but currents, you want to short them out. So with the voltage, as you're pulling this pin, make sure you pull it out really slowly. If you feel it shaking, if you see a spark, put it right back in so in order to short it out. You may have some problems with the wiring. So as you go through the sequence, be cognizant of what's happening. I've seen some sites where the electricians share the neutrals, and even though there is no voltage, usually you don't see much voltage in here, but if they share the neutral, you could have current flowing through there if they're sharing the neutral with other circuits. So keep that in mind. So you take your pins, you go through the procedure, and the last one in is your, and the last one out, I'm sorry, it's the one grounding it. Or leave it in. My practice is just leave that last one in so you know that it's there for the next guy, for the next time. Now going into the electromechanical relay testing. Confirm that the relay operated within the tolerance. Usually the testing is limited to specific relay manufacturer instructions. Know your testing equipment capabilities. There are certain test sets that have what they call a high burden mode, in which they're able to provide you more current at a lower voltage. But that higher current allows you to test this high burden coils, instantaneous coils used for electromechanical relays. So that's what I mean by know the testing capabilities of your equipment. Calibrate the components as needed, and if it's part of your job, that to me it's a separate science to know how to calibrate these things. The testing methods often used, you have for pickup, you could have just a regular staircase or ramp tool. You could do a pulse ramp in which you increase your current little by little, but you shut it off. There's intervals where there is no current going into the relay. That way you don't overheat the relay. You will use that to test an instantaneous. Binary search. This is a good tool when you don't know what the pickup of an instantaneous is or any pickup whatsoever. This binary search tool, you only have to give it a band, a big band where you think the pickup is, and then the tool itself will know when the relay should trip and should not trip, and it will narrow it down to find the actual pickup. So those are 3 tools that you could use to to do your pickup. To do timing, you could do your fault. Some tools will even have the graph and the curve, and they will show you how much time it should take for the relay to trip. You could use what they call a pre-fault or fault, where you have a pre-fault with nominal values, and then you apply the fault to measure the time that it takes to trip. And one thing to keep in mind is, especially if they have the induction disk, make sure that you allow time for the relay to reset. Sometimes when you're doing the timing and you test 2 times and then immediately you test 3 times pickup, if you don't allow time for that disk to rotate, your timing is going to be off. So one thing to keep in mind when you do this type of test is at least on certain manufacturers, it's called the reset time for the breaker. That's what they mean. And then, you know, your target and ceiling, which are your flags for your instantaneous and for your time over current. You have a separate testing tool sometimes to test those. Documentation. I have a slide on documentation at the end. We're talking about microprocessor relays. The consensus is to do a meterings check. Only test the protections that are enabled. All the others should have been done not at commissioning but at acceptance testing to make sure that those protections work. But when you're doing, let's say, commissioning or maintenance, you know, only test the protections that are enabled. Make sure that your I/O works, not only the I/Os on the relay but the wiring. The protection and function logic, all the interlocks are working, your torque controls, your flex logics, they all make sense. And that's probably what's going to take more time than the actual element testing. Make sure that the front lights and the buttons work. You know, these are all the things that you should do while you test the relays. Some common challenges that you have, you know, it's when elements overlap. Now that you have a multifunctional microprocessor relays, that it's looking at 10 different elements virtually at the same time, you know, you could have some phase faults that are going to trip on ground faults if you're doing a single phase test. You may have a 50 element tripping when trying to test a 51 element at high multiples of pickup. Sometimes certain elements require 3-phase voltage to be applied for that element to work. Otherwise, the element doesn't work. So you have to understand and go through the relay manual and understand how the relay wants you to perform that test. Some examples is the loss of potential or not loss of potential. That's very big on Schweizer relays. A lot of functions, they either have the breaker failure logic or the loss of potential logic. So make sure you have an understanding of how that logic works, the loss of potential and the breaker failure. If you have an understanding on how those functions are working, and then see how they apply those as torque controls for other elements, it will help you. Especially those two are ones that are used a lot, at least on Schweizer relays. So the big question with microprocessor relays, do you change the relay settings, or in order to test that element, you know, are you driving just for a test result, or are you driving to test the application? My advice is try to test the relay application, understand the application, and come up with a test from that. Not just isolate the protection, because when you test like that, you're more able to really understand what the intent of the protection is, instead of just driving for a result. I know it's easier said than done, but and it probably takes practice, but it's something that I think you should create a habit of. So there are different tools that are provided in relay software, relay testing software, that will help you with all this. One tool is this stabilization test. This is like a metering check. Before you go in, you got to make sure, confirm that your wiring from your relay tested. It's whatever you want to inject, the relay is receiving it. So that's one of the first things that you should do, making sure that your wiring is correct and that your settings is correct. So you do, they call it a stabilization or a metering check, to make sure that your voltages and your currents are being wired to the right place and with the right polarities. You could have other tools that check for frequency. It will do everything. Your under frequency, over frequency, your rate of change of frequency. There are differential tools for motors, transformers, bus differentials. You have advanced RAMs, knowing how to use RAMs and how to set them together to test. Let's say you're doing you could use an advanced RAM to test a 25 element, and you want to check the angles on both sides, the positive angle and your negative closing angle. You could do one test instead of two tests to test the positive and the negative and the pickup, all using one ramp. The sequencer, this is a good tool when you want to test reclosers. So you have a sequence of events that happen, and you provide the relay with different voltages and currents depending on the sequence that you set up. There are some impedance tests, and there are multiple screens that you could use impedance tests depending on what type of impedance testing are you doing. A synchronizer, this is good for generator controllers. It will allow you to see at what voltage and at what frequency. It will change it for you, and it will allow you to see when the relay closes in order to connect a generator to a system. You have a power swing tool that would allow you to simulate power swing conditions so that you could test, especially for generator protection, you could use this tool a lot. If you want to use the relay test templates, now you could, each relay tester manufacturer will have templates that have all those tests included for different relays. And it will only enable the tests that are enabled on that relay. I think this is more, to me, it's more advanced. My advice would always be understand the tools, understand the protections before you start using the templates available. Because the problem is everything is great when things work, but when they don't work, that's when you really know who the good guys are, because they understand things and they're able to troubleshoot. And that happens when things are not working correctly. So if you're just used to testing with the templates, well, you are kind of cheating yourself, in my opinion, if you don't understand the tools, the protections, and everything. There's also dynamic testing tools when you're doing end-to-end testing that could help you using COMTRACE file or SS1 files, etc. So these are different tools that you could use. Documentation, I'm gonna go a little faster because I don't have much time, but is it automatic or manual? Are you still, are you supposed to document on a sheet of paper, or are you using your test sheet? Are there any calculations done for your min and your max and knowing how the test pass or fail? So ultimately, this is one of the most important things that in my opinion, gets overlooked. The criteria for passing or failing, sometimes you have to understand what to expect and what the boundaries are for that expectation. What's the minimum and the maximum? So having documentation that allows you to see that, allows the customer to see that, it's one of the most important things, because at the end of the test, that customer is going to receive this report, and the first thing that he wants to see is that test status. Did it pass or did it fail? That's the first thing everybody looks. Then they'll look into the report. But if they don't see that green pass, you're going to have some questions, and you better be prepared to know. So knowing sometimes it boils down to knowing how to set up the boundary conditions. Some things that your documentation, in my opinion, should include the company logo, the project details, the relay nameplate, CT-PT ratios. Is this an as found or as left settings information or testing information? Obviously, if it passes or it fails, some comments, notes. Can you put pictures in it? There's some software that you could add pictures on the comments. That helps a lot. The test equipment and the tester, and sometimes the equipment calibration. Have that on the documentation. Have it ready so everybody knows. And not only for this time, but next year when you come back to test the relay, you could say, oh, such and such tested this relay last time. Maybe I have a question, you could call them. How you store this documentation. Are you storing it on a database, or is it just gonna stay on your computer? There are services out there that all your all your documentation goes into this master database where everything is saved in there. So God forbid something happens to your computer, there is a backup in a master server. So things to keep in mind on documentation. Not only have it here, but there's services available. Now I'm going to move really quick on some tips and tricks. I get a lot of questions still on how do I got to test this relay, but it's being fed by an open delta. How do I simulate an open delta connection going into a relay? So for this, I'm going to use an example from an SCL, and this is how Schweitzer wants you to wire, in this case, an SCL 700G. You have an open delta PT, and this is kind of the expectation on the voltages. You have your A and B, your voltage A and B, your line-to-line voltage 30 degrees from what would be a line to neutral. Your B and C, it's minus 90, and your C and A are at minus 120. So how would you do that with a relay test? So first of all, you inject from one channel to A and B, you would connect 120 volts at 30 degrees. So that creates this phaser right here. And you would set it up on your test set like that, 120 volts, 30 degrees into A and B. And you would wire it like this, your red, your polarity into A, non-polarity into B. The next step, and this is what the relay would see. You're injecting 120 at 30 degrees, your relay will see 120 and 30 degrees because that's the polarity that it wants to see, positive on A, negative on B. The next thing that you're going to do is you're going to add a jumper on B phase. So both the B phase on the second channel, your black terminals, you get a jumper in there, and you inject a C to B voltage into the relay. And that would be 120 at 90 degrees. So if you're an electrical engineer, your phaser will look like this. It's 90 degrees up. But bear in mind, this is your voltage C to B, and the relay wants to see B to C. So what happens is, now your relay, you're injecting voltage C to B, 120, 90, but your relay, it's going to interpret as 120 minus 90. Because that's how the relay sees it. It's going to see the voltage from B, your polarity on B, to C. So this voltage is derived. You inject C to B voltage, but you derive B to C. This is what the relay is going to see. So using 2 voltage channels, you get a 3-phase voltage. The last voltage is also going to be derived, which is going to be the voltage from C to A. That's this voltage right here. And on a phasor diagram, it will look like that. So when you move it together, you move this to the origin, and that's your 3-phase voltages on your expected values into the relay. So this is how you would do an open delta connection for a relay. Another tool that I would like to bring up, and a lot of testers are not aware, there is this fault calculators that they call them on the software, and this fault calculator has different tools that allow you to test things a lot easier. Right? It has symmetrical components, it have impedance values. In this case, let's say you're testing a non-balanced voltage or current pickup. And there are different ways of doing it. Sometimes is your negative sequence over your positive sequence, or a percentage of your negative sequence based on the nominal current. The easiest thing to test these is go into the software of your relay and look for a fault calculator. In that fault calculator, you're able to set positive sequence current and negative sequence currents, the values that you get from the settings. And this tool will automatically translate your phase sequence values. And that way you could test it much easier. It will make it, you don't even have to understand sequence components. As long as you understand the basic theory, you could apply this tool, which is in most relay testing softwares, and it will make your testing a lot easier. When I learned that, it was an eye-opener using that fault calculator. Next thing is now with microcontroller relays. you get this trip functions. And sometimes it could be overwhelming on trying to understand what's going on. So I want to show you 3 different ways to see these the same logic equation. So let's say your trip or an output contact is programmed with this function. It's a 27P, 51PT, 51N, and your 50P. And you on here, I'm sorry, I take it back. What I meant to say is I have another example with that. On this one, what you want to do is you want to test, this happens a lot, 51P, your time over current, that's 5 amps, but you also have a 51N at 3 amps. And you're doing a single phase test or a 3-phase test, and your 51N trips before your 51P trips. So how do you deal with that? Because you're going to inject a single phase test, and the relay is going to see it as a single phase to ground fault. It's going to see neutral current. So what you could do is, one quick thing that you could do is, now you inject the test value, your pickup value. Let's say you're doing an A phase fault. You inject, let's say 5 amps is your pickup for your phase, but then you use your voltage B and C, you cut it in half. So in this case, it's 2.5 of one at 180, both of them. So you split the current going on phase and coming back into B and C. So that way, this 2.5 is less than your neutral. So that way, your relay will not trip on neutral overcurrent, but it will trip on phase overcurrent. So splitting the current, you inject the fault current on A and coming back on B and C, and do the opposite for all the other phases. It will allow you to test that quicker instead of disabling this 51N protection to test the phase protections. This is one tip that you could use. And why does it work? Well, the hint is your neutral current is the sum, the vectorial sum of all these. And when you sum all that, you get 0. And that's why it works. It doesn't see any neutral current. This is what I meant on my previous example. Interpreting relay logic. And let's say you have an output 101 that has this variable logic in there. And that variable logic has this equation. Now, I'm going to show you 3 different ways to look at these logics that, at least to me, it allowed me to understand logic better, and it makes it easier to troubleshoot and understand. Number one is, I'm a math major, so mathematically, you could see this equation and you could treat it as a regular polynomial. So you do polynomial multiplication. You multiply this one times this one, times this one times this one, plus this one times this one, and this one times this one. So now you transform all these OR logics into AND logics. So it makes it a lot easier to look at a bunch of different logics, and I'm going to show you the gate logic. So this first equation, the gate logic would be like this, and for the second equation, it will look like that. So you transform a logic that had an AND with ORs into a bunch of ORs and one AND. It's a lot easier to translate a bunch of ORs to one AND. It's much easier to see it. So now you know that this equation is either this or this, and you could treat it independently. This is an OR, this is an OR, and all those ANDs together makes it. So as you decompose this equation into this equation, now you have 4. So now you have 4 different small problems instead of having one big problem. So looking at it like that and being able to decompose it helps you understand that logic. And the third way is, I started as an electrician, looking at it as contacts. It also helps. So how you would see this equation, you know, your ORs or your pluses are parallel circuits, and your multiplications and your ANDs are series circuits. So the top equation will translate to a circuit like this, and your bottom, your blue equation will look like this. So it's much easier for you to troubleshoot if you know, okay, if I only assert this and this should trip, then this and this. So you divided the problem into smaller problems. That's another way. Lastly, and I'm gonna go really quick through this, it's going through testing DC circuits. So let's say you have a 125 source that's tripping, that's controlling it, your breaker in this case, and you have your closed coil and you got your trip coil, you have an 86 device here tripping, and you have your relay contact, right? First time I was out and I was troubleshooting, I wasn't very good at understanding what voltages I should see on my multimeter when I'm troubleshooting. So I'm going to give you a couple of examples. I'm going to ask you questions to see what's your understanding on DC circuits. So let's assume in this case that the breaker is racked in. So, and in the closed position. So if the breaker is racked in and closed, this contact is going to be closed, this contact is going to be closed, this contact is going to be closed, and this contact is going to be open. That's because of the assumption that the breaker is racked in and it's closed. Let's assume that all the tripping contacts are open, and now you put your multimeter like this, right? Exactly as you see, your positive polarities and your negative polarities. Look at your wiring. What voltage would you expect to read? And it takes a little bit of time, but the answer is 100 minus 120 volts. This is what you will see on the multimeter, because the polarity that you're using, your positive polarity of the multimeter, it's going to your negative polarity of your DC. So in this case, if you put your multimeter right there, you should see 120 volts DC. Let's say right now you're checking the voltage on your trip coil, and all these conditions, all these contacts are open, this one is closed, and you put your multimeter to measure the voltage across the trip coil. What voltage would you see? Would you see 0 volts, 120 volts, or minus 120 volts? The answer is 0 volts, because you got positive DC coming up to here, and it stops at the contact. By your negative DC voltage, there is no voltage drop on the trip coil. There's no current flowing. Therefore, the voltage drop across that trip coil at this moment, it's at 0. So you should read 0 volts. I think I gave you the answer already. Let's say now you're testing your relay, and the moment the relay trips the breaker, this contact closes. The moment this contact closes, and let's say you left your meter from last example, and you want to see the voltage at your trip coil, what voltage would you expect to see? And the answer is 120 volts on that, because now your positive voltage comes in. This is a short circuit. It goes in here. Up to here, you got positive. Now you're going to have a voltage drop in here. So the moment that contact closes, you're going to have 120 across that coil. So now at that same moment, let's say you have another meter, but now this time you're looking at your closing contact. What would you see across it the moment that it closed? And the answer is 0 volts, because now your voltage drop is here, and this pretty much becomes a short circuit. So you should see 0 volts in there. If you don't have this understanding and you want to troubleshoot DC circuits, it's going to be a problem. Now, in conclusion, I gave you a framework from a personal experience on how I took not only relay testing, but electrical testing. We went into the defining the test types, the area of responsibilities, the types of relays, the tools that you need, what to do during site arrival, during testing. I gave you different tools that you could use. And the last message that I would give, or the last advice I would give for new relay testers or engineers, is start by manually testing every function before using the automatic templates. You know, try to understand the function, trying to understand the test set, trying to understand the software and the tools. And you know, the best testers have a good understanding not only of the relay, but the whole protection scheme. So you don't have to be an expert on everything, but have general knowledge, or acquire as you progress in your career. Try to understand all parts of the system, not just the relay. and test the application, not just get the results. That will really separate a good tester from a not so good tester in my eyes or in my opinion. And with that, I'll leave it up to questions.
All right. Thanks, Guillermo. So as mentioned, the presentation portion of our webinar is concluded. Thanks again, Guillermo, for putting together such a tight presentation. A lot of great information there. A lot of people really appreciated it. I'll let you pause your screen there for us to get into our Q&A session while we try and answer as many of your questions as possible. For those of you in our audience still, if you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there's also a field for you to request a quote or demo on any Megger or PowerDB products. A copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars, and register for our webinar on February 18th, titled Understanding and Interpreting the Time Domain Reflectometer Traces for Cable Fault Location. That will be presented by Joseph Aguirre. All right, so let's jump into our questions. The first one I have, I'll be directing to our panelist, Sughosh Cooper. Sughosh, how do we ensure the relay testing mimics real-world events, i.e., faults, and not just the testing of elements in a vacuum?
Thank you, Michael, for the question. So it's a very good question. So for you to mimic a real-world condition, it's a real-world fault condition. Obviously, the system that when you work with a setting, the system would have already been modeled. Your power system is modeled in the simulation software. And certain studies are done before protection engineer comes up with the relay settings and provides those relays with the settings for testing, right? So when you model this system in the software, you can simulate different fault conditions in the system, different type of faults, different location in the system. Wherever you want to actually simulate a fault, you could do that, and then you can export the ComTrade format file from the software. So these ComTrade files would have the test values to mimic the fault that was simulated in the software, right? And when I say these test values, it's nothing but your currents or voltages or combination of both that would be present in the ComTrade file. Okay, once you get the ComTrade file, you could play that back to the relay using a relay test equipment, which in turn would mimic a fault condition similar to a real world condition. And you can call this like a dynamic mode of testing because it's pretty close to a real world condition simulation, right? So you could do that. You could also export these different fault simulation scenarios in the form of a SS1 file from the software. And again, these SS1 files, they consist of all the fault simulations which are built as state sequencer tests. And these tests, these particular tests are, in the form of states. They can be injected to the relays, which again mimics the fault conditions that were simulated in the software. So, by doing this, basically you're not just injecting some current or voltage just to check a setting, but really trying to simulate a fault condition based on the power system studies that was performed on your system, and seeing how your relay would behave for that kind of fault. So yeah, I hope I answered your question.
Thanks, Sughosh. Moving on to our next question for Abel Gonzalez. Abel, if you are testing relays in a substation, do you have to test the CT and VT as well?
Hi, hello, Mike. Can you hear me?
I can hear you.
Okay, thanks. Yeah, that's a pretty common and very good question. It depends. It depends on the scope of work, like Guillermo mentioned. Sometimes when you're testing relays, all you're doing is some maybe forensic test on the relay to see if the and the only thing that you have isolated is the relay, and those CTs and PTs that are used for that relay are used for something else, and you don't have access to them. But when you're doing maintenance, for example, in a substation, and you're doing maintenance on the whole substation, you definitely need to test the CTs and PTs. They are the eyes of the relays. So the answer is yes, you need to test the VTs and PTs. Now, is it the relay tester, the guy who's testing the relays, doing the CT and PT testing? Sometimes it is, sometimes it isn't. But the answer is yes, you do need to test it, and it will depend on the scope of work and your access, the access you have to the PTs and VTs, and especially it's important to test the CTs after you have a fault or there was a trip on the relay, because a lot of times those CTs after a fault, given the asymmetrical form of the waveform of the current, the CTs remain either magnetized or with some sort of magnetized residual magnetization flux on the CT, which means that the CT is not going to give you reliable information after. So you definitely need to test the CTs after there was a fault in the circuit that CT is measuring. Okay,
Bill?
that answers it, I guess.
Yeah. I'm going to throw things back over to Sugosh for our third question. Is it the responsibility of the tester to verify that the settings are correct?
Well, it's I would say it's kind of open-ended in the sense that it's not. It depends on the scope of work, of course. But as far as I've seen, as I've come across so far, whenever I've been to the field for testing protection systems, right, it's usually not the responsibility of the tester to verify that the settings are correct in the sense that they are reliable and accurate enough that would protect a system. Not really, no. But it's a good practice if the tester can, like Guillermo was explaining in his slides, if a tester can recognize that a particular setting, it does not look right, it could be underprotected. It could be set wrong. There could be a miscoordination. Maybe the instantaneous overcurrent pickup is same as your time overcurrent pickup. So these are certain things. It's good to be able to do it, but not necessarily is a mandate thing or mandatory thing for a tester to let the customer know that the settings are correct or no. So the responsibility of the tester, on most times would be just to test that relay for the settings and provide a report which shows that if the relay is doing fine for that setting or no. Another thing I would like to add here is about one thing about the settings when it comes to tester is it's important to make sure that the as found and as left settings are matching after the tester has performed his testing. But going back to the original question, not really the responsibility. Like I said, it's good to know if the setting is wrong or no, so that you build an image with the customer, you build a reputation, you let them know that you are knowledgeable in this field, but not really when it comes to mandatory things. So.
Thanks, Sugosh. Back over to our presenter, Guillermo Falquez. Guillermo, does Megger provide license to PowerDB software?
Okay, you could hear me, correct?
Correct.
Okay. So Megger, specifically the RTMS or PowerDB software so PowerDB is used to test. It's a software to be used with many different Megger test equipment. So you have CT tester, all kinds of testers. So the software that we use to test relays within PowerDB is what we call RTMS, or Relay Testing Management Software. And that software, there's 3 levels. The basic level, it's free of charge. You could go to our website, create an account with Megger, and you could download it free of charge. You could play with it. It has a simulation mode, and you could use all these tools that I showed you within my presentation, we could spend more time if you need an explanation on how to use them or where to apply them. That's our job, Abel, Sugosh, and my job, and we're here to help you. I just went through a quick overview, and within the free software, you could use all these tools. Now there is two other levels, which is the advanced and the pro. The advanced is not used much, so I'm just gonna skip right through it. But the pro version of it, it talks more with the documentation and how you could have a database sent with all your testing results into one giant database, a server, where let's say your whole company saves your files. So that would be a PowerDB Pro version. Within RTMS, the relay testing management software, there are different tools, more advanced tools that are available and that are enabled at an extra charge. But the basic tools, and I'm gonna go out there and say probably 95% of all relays out there, you're probably gonna be able to test them with the basic tools. So long story short is yes, we do provide it free of charge at a basic level, which should be sufficient for 95% of the applications out there.
Excellent. Thanks, Guillermo. Over to Abel. Abel, how do you test voltage operated overcurrent and residual neutral over voltage?
Okay, thanks, Mike. Well, these are two different, well, we could even be talking about three different protection functions here. When I understand when talking about voltage operated over current, we could be talking about voltage restrained over current, or we could be talking about voltage controlled over current. This second case, the voltage controlled over current, the way it works is it's a regular overcurrent function. It's only torque controlled by a voltage, an under voltage element. So if the voltage is below a certain level, the overcurrent function doesn't operate. If the voltage is above a certain level, it's a regular overcurrent element. So all you need to do is make sure that you verify that the overcurrent function is blocked when the voltage is lower than X. So what you would do is you would apply an overcurrent condition, but you would at the same time inject the voltage lower than the voltage threshold for the voltage, the torque control, and the overcurrent shouldn't operate. And on reverse, you would inject a current value that's higher than the pickup, and at the same time you would inject a voltage that's higher than the torque control, and that 51 or 50 element should operate in that case. And then you can test at different multiples, always keeping the voltage higher than the value of voltage that you want to. You can do that either manually or you can do it automatically with the tools available, like Guillermo said, in RTMS. Then there's the voltage restrained over current element, which will trip at the same times as the regular overcurrent element, except the pickup is, in this case, restrained by voltage, and the lower the voltage, the lower the pickup of the current. You have to find for the particular relay that you are testing what is the equation that is used. In a lot of relays, it's just a linear relationship that goes from the pickup, a minimum value of voltage, to a nominal voltage. At nominal voltage, the pickup of the overcurrent is the nominal, the regular pickup of the overcurrent. As the voltage drops, the pickup of the overcurrent element will drop. So what you would need to do is you would need to inject voltages lower than the nominal, and at the same time you would check that the pickup that the 51, let's say, element has at that voltage that was lower than the nominal is, in this case, lower than the regular pickup of the overcurrent, and that the percentage corresponds with the manufacturer specification for that particular function. In some cases, it's the same, so that if you drop the let's say the voltage to 50% of nominal, then the pickup of the 51 will drop to 50% of nominal, and so on. In other cases, the relationship will be skewed to one place or the other, and the settings in the relay will tell you what to do in that case. In the case of the well, that answers the overcurrent elements and how you would test them, right? In the case of the what was the other one? Let me see. It was the
Residual neutral over voltage.
Oh, residual neutral over voltage. Yes, I'm sorry. Well, there are tools. I think Guillermo showed them on, if we're using RTMS or any other test software out there, I guess they all have them. But in particular in RTMS, you can basically set the 3V0, which is the residual neutral over voltage. You can set directly in the home screen. You can say, I want the residual to be this value, and the software will calculate the values of the voltages on the three phases that will produce that over voltage on the neutral. Another way of doing it, which is not maybe as sophisticated, is to put two voltages at 0, and then the other voltage will basically become the residual. But there are logic constraints in the relays that will sometimes prevent the element from operating if the voltage disappears from two of the phases. So creating an unbalance, I guess, is the best most sure way to test that function. And again, it all comes down to how the relay logic that controls that function is implemented at the relay that you are testing, because it's not every relay, and I mean not every relay implements that function the same way. I guess that answers the question.
Thanks, Abel. Over to Sugosh. Could you please explain more about binary search in further detail?
Okay. So the binary search technique is used to determine the pickup value of a relay, and it's used to do that quickly. Faster way of determining the pickup value of a relay, which could have like a questionable set point or like an unknown setting, basically, because you don't know the setting of the relay. For example, your instantaneous setting on electromechanical relays, you would have to look at the scale, but it's most of the times not accurate on the scale as to where the screw is located, right? And then you would have to either go back to an older test report to see what was the value at which it was tested last time. If you don't have that, then it's basically unknown setting for you, right? So that's when you could use binary search. Basically, here what happens is that you could say that you could give an assumed setting value saying this could be a value, or you could say the expected is unknown. You don't know what the expected is, right? So and this is like a ramp technique, which is like a pulse ramping, but in the method of binary search. So what happens here is you don't provide an increment for the ramp. Usually you provide an increment value for a ramp, but here you would provide an end resolution value for the final search increment. Okay, and you would obviously have a start percentage and end percentage, or a start and end value. Of course, you would know the range of instantaneous for that setting on a relay. You would know that it's between 0 and 70 amps, and then you don't know where the setting is in between. So what happens is, if you have a pre-fault already set, the first output that is injected would be a pre-fault setting. Then it pulses to the fault value, right? And if an operation of the relay occurs within the pulsed time, right, the fault value output will automatically increment down by 50% of the difference between the last operate and the no operate. So basically, let's say, for example, you have the range of 0 to 70. So it first injects a value of 35 amps in between, okay? And then sees if the relay trips or not. If the relay trips, it means that it has already crossed the range of tripping. So it now changes its range from 0 to 35 amps. So on and so forth. It keeps on changing the range until it hits an end resolution of, let's say, 0.1 amps or whatever you specify. And it's basically bidirectional, right? It goes back and forth, and it's pretty fast in finding an unknown setting. So that's about binary search.
Thanks a lot. Our next question is going back over to Guillermo. Guillermo, why not just mask to a different output?
Yeah, and that goes back to the are you testing the application or are you testing to find a result? Uh, there, let's begin with the fact that the engineer in charge of the settings, he mapped to that protection to that particular output for a particular reason. Let's hope that that's what happened. In a perfect world, that's what it's supposed to happen. Usually when you're doing a test and you have different functions, from a technician or a testing engineer, the way I see it is if I change that output, yes, I will get a result and I will find out what I'm going to find out what I want to find out, what I'm looking for. I'm going to look for that pickup, or I'm going to find that testing time. However, and this is going back to what separates a good tester from a not so good tester, is if you are testing it as it is applied, and I understand sometimes there is no other way around it, if you have to have a result, but if you want to test the application, then maybe you're able to find out something that, let's say you're testing one element and another element trips that output. So maybe you found a mismatch on the protection, and maybe you could go back to the engineer and say, hey, I'm testing this element, but this other element is tripping, but it's really not making sense. Maybe you should change this element to another protection. So you, in a way, are you're supervising the settings. I mean, if you want to take it to the next level of testing, so you could come with settings mismatch. You could come up with or find out a coordination mismatch. You could take really your results to a next level if you test the application, you test the settings as applied, and not create a whole different test plan just to drive for results. That's kind of like a philosophy question, and I would leave it up to each tester. But in my opinion, you should really focus on testing the application, because you might be able to find out more about the protection, find out problems, and also becoming more valuable to your customer or your company, because you took the extra mile to do it. I hope that answers that question.
Thanks, Guillermo. I know we are a little over time, but we're going to try and knock out a few more questions because naturally we have a lot of great questions from our audience today. So we'd like to try and give it the time that it deserves. So we're going to go on just a little bit longer and take on a few more questions. The first of which is going over to Abel. Abel, should relay element specifications be used as the minimum and maximum range for the element to be used in a pass condition?
That's a great question. Typically, we should test to the manufacturer's specifications for the relay. Guillermo mentioned that the utilities they test the relays before they allow them in their system, which means that the relay specifications as they are published have already been accepted by that utility to use the relay in their system, and therefore we cannot expect from a particular relay a behavior better than the one that's in the relay's specification. That said, we could expect a worst behavior from that relay if that is allowed by the customer in the place where that relay is installed. In my experience, normally customers, once they have and I'm talking typically, industrial customers and whatnot, they have the relays installed and they typically don't pay a lot of attention to that. They trust whoever installed the system, and they don't even have a lot of times policies regarding that. So you have no choice but to go to the relay specifications. So to answer your question, I believe the best way to do it is to look for local guidelines, if there are any, and if there are no local guidelines, then go with the manufacturer specifications. Okay, that would be my, and yes, if you have the manufacturer specifications, then it's usually relatively simple to come up with your minimum and maximum values for each of the different elements that you're testing for each of the protection functions.
Thanks,
Okay.
Abel.
Yeah, that sounds.
Yeah. Over to Zagosh. Is the RTMS software, in the RTMS software, is there a template for stability test results?
Okay, so there are a few places. So when we talk about stability test, pertaining to, let's say, differential relay testing, right? So in RTMS software, on the differential test screen, once you input the relay settings and move on to the test screen, the first test that appears is the stabilization test. So wherein it would automatically be ready to inject winding 1 and winding 2 current, and then also it would have a place wherein you can enter what current readings were metered on the relay, winding 1 and winding 2. And then there also like a place to enter the differential current and the operating in the restraint current. That is for differential, right? But now let's say if you want to do a metering check, right, to make sure your wiring and connections are all correct, there is a separate screen for. Hello. So there is a separate screen wherein you could enter your CT ratios and PT ratio, and then you could inject certain currents and voltages, and you could, once you run that particular test, it reads the metering values from the relays and displays that on the screen and tells you if the whatever was injected was metered as it was expected to be, and it tells you if it's a pass or fail, which will tell you that your connections are good and your wiring is good and whatever you're injecting is fine with the relay.
All right, thanks. We'll move on to one last question here. With the belt, how often does a relay need to do a maintenance test per your experience?
Well, that's also a very interesting and very often asked question. And unfortunately, there is not a single answer to that question. It depends on many factors. First, what type of relay are we talking about? Is it an electromechanical? Is it a static solid state relay? Is it a microprocessor relay? How old is the relay? How long has the relay been in operation? Where is the relay installed? What's the criticality of the system that relay serves? What are the local regulations in the area where that relay is to be tested? All those things have to be taken into account when designing and implementing a maintenance schedule for relays. Of course, electromechanical relays, they need to be tested more frequently than microprocessor relays because of the nature of the manufacturing of those relays. Microprocessor relays, you would think that they don't need any type of maintenance, but right now in the current environment, where we have all these, computers and all these computing, related requirements and all the network verifications and networking related tripping and things like that. One thing as simple as checking the relay settings and checking that and verifying that the relay settings correspond with the approved relay settings, because somebody could have come to the relay and unfortunately not a lot of people use passwords on the relays. Someone could have come to the relay and changed the settings, and either intentionally, maliciously, or unintentionally, the relay could be in a status where it's not doing the protection that it's supposed to do. Something as simple as that should be checked periodically, even in microprocessor relays. So again, it depends on a huge number of factors. So unfortunately, there is not a single answer to that. My recommendation is check with the local regulations, and when I say local, they could be in your state, in your country, but it could also be in the factory. Maybe the factory has a policy that requires the factory to test their. I know that some factories that they do check their relays and they perform maintenance on their substations once a year. So, and in some other places they do it once every 2 years. So in some places they are more restrictive than the general regulations in their state or their province or even in their country. Okay, so I guess that would be the answer to that.
All right. Well, it looks like we've blasted past our time for Q&A session today, but we do apologize if we didn't get to your question live. We'll be working to get with you offline to answer those questions. As a reminder, we will be sending out a copy of this presentation, your certificate of attendance, and a link to the video recording of this webinar in about 2 business days. I'd like to thank you all for attending. However, we're very excited to kick off our new year of educational webinars. After we conclude here, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested, as well as a field to let us know how we did and topics we should cover this year. But once again, I'd like to thank you all so much for attending, and I hope you all have a great weekend.